Hello and welcome back to real-time rendering here on the Lötwig Fusel channel. Now in the last video we have talked about geometry on the GPU. It was just a PowerPointy video where we discussed on how the GPU works, how all the theory works, that we need triangles and what we gonna call the kind of like points of the triangles, that we gonna call them vertices, that we can store data on the vertices, and we did a lot of interesting video, but really we didn't get forward in terms of actual getting hands-on and learning how to write code for that. And that's what we want to do today. Today we actually want to jump in and write some code that is going to import any arbitrary three-dimensional mesh from a content creation software like Blender into our own context. And for that, I've actually opened up Blender so that we can start and author a nice little 3D model. Now, Blender, you do not need to be an expert on Blender. Actually, the three-dimensional model that we are going to use, it's going to be included in the repository, so it's not really required. Now, if you are clicking away that startup window, I don't know how I've managed to click it away, probably just because I've clicked outside of that window and then it disappeared. You're going to get the cube, right? We could take that cube here, export this straight away. It's a default Blender cube, and use that one as a demo asset. However, I personally find that cube is really uninteresting. It's not looking good, it's not interesting, it's trash. We want to delete it, it's not looking nice. Now, what we could do now is we could start and create our own mesh, right? We can like say add, and we could add a curve, text, volume, surfaces, a UV sphere, configure that, like scale that around. Or I am a total Blender noob. I completely pressed the wrong button. I know what I've done. I don't know, but I don't care. It's just gonna reverse until I'm done. Right now I could go in here and create amazing stuff if I would be good in such things. However, I'm not. So I need pre-created assets, and Blender is providing us a asset that we can tinker around with. We can do this by clicking on Add, Mesh, and then we're gonna select Monkey. If we hover over that, construct a Suzanne mesh. If I click on that, we get Suzanne. Suzanne is Blender's kind of like demo monkey. It's available in many versions. I think, like, is it also here, for example, in like this this like drawing two-dimensional style. So Suzanne is kind of like, they like it. Blender really likes Suzanne. And if I press and hold Alt and move my mouse around, I can also click and drag my mouse around. I can also like inspect that mesh and take a look on how Suzanne looks. And you can see we get this nice little monkey out of some geometry. Now, I'm explicitly saying geometry because if I would say triangles, it would be wrong, because Suzanne is not composed out of triangles. That's a big drawback of Suzanne, or in general, three-dimensional content software. Because software like Blender, they don't care if meshes are triangular, if they are not, if they are quads, if they are even higher orders. Applications like Blender, they really don't care. They have invested into algorithms that can render any kind of like geometry imaginable. Not any, there's also constraints, but they can do it, right? It's not a problem for them. However, it's a problem for us because we want to do real-time rendering, and for real-time rendering, we need to optimize everything. So what we need to do is we need to optimize every mesh that we get into a triangular mesh, or at maximum a triangular mesh. Point clouds would be even better to use, maybe. But what we need to do is we need to have every mesh as triangles. Now, as you can see, Suzanne is not composed out of triangles. I mean, the eyes here, they are triangles. You can see there's a center point, and we have two other points, 1, 2, 3, triangle. However, for example, directly next to it, like the kind of like the hole for the eye, it's composed out of quads. 1, 2, 3, 4 is one surface. If I would go into like, where is that? Edit mode, layout, modeling, sculpting. Is it, I think, in modeling? Yeah. If I go into modeling, you can actually see and drag on all of these things. I can put this into face mode, I think. All right, so if I press 2, no, 3. Now you can see that I can select these faces, right? The number 3. I had to press the number 3. And then you can see that, for example, like the eye here, this eye here, it is a triangle. That one seems to be a triangle as well, but all of the other things, they are quads. And that's good because they can do way better modeling, especially if you're an artist and you are like in this editing mode 1, and you can select like an edge. You can way easier transform that monkey and make it look worse. or better, depending on how you want to call what I'm doing here. Probably if I'm doing it worse. But you could give Suzanne like this notch. It's way better because it's like composed out of quads, and quads for an artist are better to use, or probably better to use than like triangles. However, we need for our rendering, we need triangles. Now there are multiple ways of solving that issue. The first issue is solving it directly in Blender. So what you could do is you could tell all your artists and all the people you buy 3D models from, you could tell them that they shall produce triangulated meshes. And it's not a problem for them. They just create Suzanne out of nowhere, out of their mind, out of their imagination. Then they go like to these modifier things and they add triangulate. They just typed in triangulate and there it is. And now you can actually see that Suzanne has now become triangulated. If I go to like modeling, it should be quads again, right? No, still, no, you can see, right? If I go to that, you can see that you can see like the original bounds. You see the original bounds and you can see the triangles that have been created by Blender. That's one way of doing it, right? There's a way of doing this, simple like that. You just say triangulate and Blender is going to triangulate everything for you. However, this is not what we want, so I'm going to remove the modifier. Why do we not want to do this? Well, because we cannot rely on that, right? If we are writing a rendering system that needs to have a triangulated mesh, it's bad, because if somebody forgets to triangulate, you need to call them, tell them to redo their meshes, maybe restart like texture painting, and there are many fallbacks if you need to rechange the mesh just because there was a communication issue. And since we can always, since we have the 4 vertices and 1 quad face, we can always convert this to triangles without issues. If we are doing it in Blender, it might even give us more issues, because Blender tries to be smart and maybe tries to interpolate some properties, or does not duplicate the properties, maybe applies if it's a curve some smoothing or something like that, and there might be things happening that we don't want. So what we in general want to do is we want to support any arbitrary mesh to import it, even though it is not triangulated. And luckily Assimp has an option for that. Assimp has many options. The nice thing on Assimp is that it supports many things and many formats, many options, and so we actually do not have that problem, but I just want to kind of like raise awareness of that. Alright, so if we have Suzanne now created inside of here, we now want to export her so that we can use it in our rendering. So what I'm going to do is I'm going to go to File, Export, and now I have many options. Now I'm going to today show you 2 options of exporting this. We're going to start with Wavefront OBJ. OBJs is a very common format. It's not very complicated and thus very easy to use. Now I want to put it in the app directory under Projects, Example, Data. You can see that Suzanne is already here, so yeah. But what I want to quickly do is I want to quickly open this up, copy the path, and now I want to actually delete Suzanne out of here. I had her in here for some testing purposes. Now, to bring Suzanne in here, I go now to Blender and paste in the path. And now we should be here. And now I'm going to call that one Suzanne.obj. Press Enter. Now we are ready. Now you could specify a few things. This is important when we are... when we are later on like importing this correctly into an engine, that like all the coordinate systems are correct while exporting. The up axis is the y axis. This is exactly what I want. The forward axis, so probably the axis that goes towards me or into the screen. That's not a big thing. But I think we're just gonna keep it on minus Z. It could be that we need to have it on Z. Positive Z axis, maybe this should be positive Z, but for now it really doesn't matter if you're doing this. Later on, if we are having like awareness in our system of coordinate systems, then we need to do this correctly, but these are kind of like, yeah, showing you a few things. You can also say like apply modifiers. If we would remove them, triangulation would not be even applied if we would have this. You can see that we again have actually the option to triangulate the meshes, and we also have the option on what we want to export. We could export normals, we can leave that in here, and UV coordinates, yeah, they're not gonna hurt us. You can also see that we want to export the materials. We do not have materials, so I'm not going to export this one. And everything else is not really required. You could like smooth and group stuff, but we don't want to do this. We want to have this very basically. Export wavefront OBJ. Gonna click that button and finished. We do not have any text that shows us that it's finished, but it should be done. If I go into the data folder here, Susan is now in here. You can see Blender 3.4, blender.org, O Susan, which stands for object. And you can see like V is a definition of many vertices. You can see like every V stands for a vertex. It's all looking in the same format. Always contains out of 3 components, X, Y, Z. And if we scroll down a bit, we should have VN. VN stands for vertex normal because we selected that we want to export normals as well. This is now basically giving us all the normals that we have. Then we have VT. VT stands for texture coordinates. You can see that normals are 3-dimensional because it's a vector, and texture coordinates are 2-dimensional because it's a 2-dimensional coordinate, which could also be seen as a 2-dimensional vector. But yeah, that's it. Then we have S and T. I'm not quite sure what S is. O is whatever. I know, maybe because whatever. But in this case, like F stands for phase. Now we are basically defining a phase. I don't know what the format here on that is. It should in general just connect vertices together. Actually, because they are chord mesh, it should connect 4. Seems like it kind of like, I think I see what's going on. It is specifying for each like vertex that it's connecting, it's like specifying probably the vertex normal and the vertex texture coordinates so that they are linked properly. And you can see that we have multiple phases here. Some phases have 4 vertices, some phases have like 3 vertices, and do we even have more? No, probably not. But you can see like that it's all like exported in a human readable and quite bloaty format. Like this OBJ file, it is as big. It has like 2066 lines, each containing many ASCII characters. And that's the main fallback of OBJ, why you don't use OBJ normally these days, because OBJs are just big. I mean, they are human readable and they are easy to parse, right? It's an easy file format. You could easily write an import algorithm for them without any issues. You could write an own generator, import OBJ without even using Assimp, just by iterating through this list, saying, all right, object Suzanne. And I probably don't know for what that down here was, because you could have multiple objects. And then down here, when you're doing like the phases, you're linking them together and you're kind of like referencing S1. So kind of like surface for object 1. But yeah, you could easily write an importer for that. It's not an issue. It's quite simple, but we don't want to do this because we want to support multiple formats and not only OBJ formats. All right, so now we have Suzanne in here, in the data folder. And now we need to define a resource for Suzanne. You can see that I already have created a demo resource with that resource.json, since we are not like having a proper way to edit them yet. And I want to quickly just walk you through. I think we already talked about these when we talked about the file formats, but yeah. This has changed at least a bit. Now we can see that there's a mesh triangular, which is sort of mesh example 3D mesh. Maybe we want to call this now Suzanne as well, since this shall persist. Suzanne. Right, mesh Suzanne. Now we have stored Suzanne a bit more meaningfully. Now, you can see that we are using like generators, and I told you that we have 3 generators. Now, since I've changed a few things, it's actually gone down to 2 generators. We're going to have 2 generators, one for importing the mesh and one for uploading the mesh. Importing is just done in the editor and baking, and uploading is done in the editor and runtime. And you can see down here, we are using like properties with the model file Suzanne.obj and the mesh at index 0. Now, this is the index that we also had in the obj file, because there could be multiple things in here, right? Now again, I'm of course down there. But here, O Suzanne was the object Suzanne, which was defined at position 0. And somewhere down there, the faces referenced by the index 0, surface 0, whatever this means. I don't know if it really means surface or select 0, whatever. But you can kind of like see we have like put everything at the index 0, and that index 0 is what I'm referencing here to import the mesh at index 0. Now, let me quickly get rid of a bit of these caching stuff so that you can see that they are actually created when I show you how the system works. And let's now actually go into and write the code for that. All right, so now we are in Visual Studio, and I want to quickly walk you through what has changed in the main file. And the main file has now two calls on initializing the system. First of all, the log manager, which is just responsible for producing nice SPD log output, managing loggers, managing syncs and stuff. That needs to be initialized. And then what we also need to initialize is the file system. In this case, I'm initializing this as a physical file system since we also want to support shipping. There is, of course, also a init as virtual file system, which would need a path to a like content.pack64, which is a special file format inspired by the Doom pack files that I have just altered a bit so that it fits for me. But in the editor, we only gonna use the init as physical file systems. By the way, the editor and the library code has now become its own project, and we also have like the tooling, which is not implemented yet, which later on shall serve the purpose of just exporting and generating packaging files for consumption during a proper run of the application. Now the idea is quite simple, right? We have the init function, init functions on the top here to initialize the systems. Then what I'm doing is the project context stuff, so I'm opening up the current project. Now after that, I need to register the generators, so the generators that are used for importing the object. In this case, the import triangular mesh and upload triangular mesh. It's not implemented yet because the generators are not there, or I have explicitly deleted them again so that we can implement them. And what I've done, added down here is I've added some code that is debugging the generators. It is just quickly generating a pipeline state here, so the generation pipeline. It's a class that handles pipelining of generation, of invoking the generators. Currently, caching is not supported, but I'm going to implement that one. It's not much that needs to be done, but I wanted to get that video out so that we at least have a bit of regular content. And I even told you that we are not concerned about how caching works in the video series. So if you're interested in that, you can dive through the source code on your own. Now you can see that I need to call generate on the generation pipeline to start the generation of one resource. In this case, I start the resource for the second element of the first resource of the context. The context is the project context, which has resources loaded. I'm just going to get the first resource, and this is like called a resource, an RTR project resource reference, which is kind of like the resource definition. That's all the data that we need to know to generate it. The only second parameter that we need is the pipeline that we want to invoke. Currently, I'm invoking like the runtime pipeline. We should like for now invoke the editor pipeline so that we are kind of like in the editor's state. Now down here, what I'm doing is I'm creating one of these pack files. The pack file is it's just a virtual file system, right? So that you can ship your data later on and ship the optimized data actually. And what I'm doing here is I am creating like the UUID from that resource that we have just generated. I'm creating a pack creator. Every pack file needs a UUID. In this case, I'm just using the system generator to generate a UUID for that. And what I'm then doing is I'm going through my requirements, get target requirements for resource. What the generation pipeline is doing, it is caching the requirements for the configuration's runtime. This is why I had runtime in here. It needs to be the runtime configuration because we only want to package the files that we use in the runtime. If we are in the editor, we might have more in there, more toolchains, more stuff that happens, and we don't want to use these. We just want to later on use the ones that are in the runtime, so only runtime ones will be cached and be retrieved by that function. But if we are doing this for the runtime, we are getting all the requirements that are required. This is all done automatically, and that's the amazing feature. You're always going to use, if you are using the generators, you're going to get a context which you are working with for like opening files and stuff, and this is automatically registering which files you are opening and automatically adding them to the requirements list so that they can automatically be resolved after kind of like simulating one load step with runtime later on in the tooling. So every time we are kind of like shipping our application, it's loading this in the runtime manner. All resources are loaded as if it would be the runtime that is loading it. They are all being loaded, and then we have a list of files that we need, and they are added to this pack creator by calling the add file function. This is currently very hacky, and is going to be like excluded into proper functions later on as well. And then I'm just writing them to a hard-coded output.pack64 path here. Now this is kind of like the flow that's currently happening. So what we are doing is we are initializing the system, opening the project, running the generators, and then packaging. Now what we need to do is we need to actually now implement the generators. Now our generators shall go into a folder called generator. So we have a folder core, which is kind of like the core implementation of what I'm doing. We have the folder infrastructure. These are like the help stuff that is not really like serving an engine purpose, while the core is serving engine purpose or top level engine purpose. Infrastructure is kind of like more general support stuff, and core is like proper systems for the engine, for example, like the project system. Now the resource system is like a top level system that you want to interact with, so that's why it is in the top level, while infrastructure is more kind of like the lower level that's backing up all these systems. Now later on, we of course also going to have a runtime folder, which is just going to include like all the rendering runtime stuff. Now, in the generators folder, I want to create all the generators. I want to now write the generators for triangular mesh. That is kind of like the generators that I want to now write. And what we want to write is we want to write the generator import triangular mesh. I want to prefix them with G import triangular mesh, like that. And then what I want to do is RTR generators. And then I want to have my class G import triangular mesh. Now, if we want to import a generator, we need the base class that we want to implement. It's stored at RTR, core, resources, resource generator. Now the G import triangular mesh is then a public resource generator, and it's stored in resources, so it's a public resources resource generator. And what we want to now do is we want to implement a few functions in here. Before I'm going to do this, I'm going to create a new file here so that we have this separated into C++ code. Now let's implement the virtual methods with Visual Assist. You can also type them down by hand. They are simply defined like that. And what you can see here is that a generator has a function getName and the function generate. The function getName, it's really simple. It shall just return the name of the generator, since there's not a proper way to retrieve the name of a class or the kind of like bound name of a class. So what I'm just going to do is I'm going to return import triangular mesh. That's just required to properly register the generator. And then what we also have is the function generate. The function generate returns a Boolean value, which shall be true if the generation was successfully and false if the generation failed. Now you can see that we have two parameters. We have the properties. These are the properties that are stored in the JSON file. So these things are just passed in as a const reference to a JSON object. So I'm not really bothered parsing them. I know that I have parsed them into unordered maps, but I've decided to revert this to not parse them as unordered maps because there's really no point. We can just put in the raw JSON properties. Now the second parameter that we are getting is the RTR resource generation context. The generation context is the context for the resource generation that we need to use to kind of like gain access to the data. For example, if we now want to open up our Suzanne.obj file, we shall not open this by like calling something like ifstream or something, or for the Windows create file W function. No, we do not want to use these ones. We want to use the functions from the context. Now you can see that the context offers a few functions. It offers a allocate output data function, a create output path, get consumers, get consumes, get logger pointer, set logger, and open. Get logger, these and set logger, these are just having something to do with logging. For example, if we want to do logging in a generator, we shall always get the logger from the context and log to that, right? Starting triangular mesh import. This is something that we shall always do with the context. The context is like having the logger attached to it. But what we also have is like this get consumes. This get consumes is nothing that we shall be really interested. This is just the way so that the generation context can be read after it has been dealt with the generators. We are only concerned in the open function, create output path, and allocate output data function. Now the open function is simple. This one is opening a file or a resource. This might not come from a file, but it's always treated as a file, and you can see that it's returned as an RTR infrastructure file pointer. So what I'm just going to do is I'm going to declare this one with output, and I'm going to call this one geometry file. And this one shall be equal to context.open. What do I want to open? Suzanne.obj. Now, of course, I need to return something. For now, let me return false because it failed. So let me for now do it like that, and let's now put a breakpoint in here and let's try to debug that. First of all, we need to include the generator, because if I'm doing it like that, which shall not work because the generator is not defined, right? We have just created the class, but it's not registered. We can quickly try this out, but we shall get an error message there, and it shall not be invoked. If I'm checking now the console, you're gonna get a bit of an output here. You can get an output first from the pieces. The pieces is the project system. It says opening project, documents, whatever, example. So it's opening up the project. Then we are getting an output from the file system Win32 because we're using the physical file system. Physical file system has been rebased to the same directory than where our project is stored. This is just used so that we are always accessing the right files if we are opening files for resources. So that the file system knows where to find them. Now, after that, we are getting a few outputs from the rgen. The rgen is the resource generator. You are going to get the output here, collecting a generator to run of configuration editor for resource whatever. So this is the resource ID of our Suzanne resource. The configuration is the configuration editor. So it's generating like these informations. And you can see that we are using the generator import triangular mesh and upload triangular mesh. Now, after that, we are getting another debug message executing two generators for resource. So now it's telling us that it's going into the execution phase and it's trying to execute two generators. And then we are getting an error message, generator import triangular mesh not found. And then from the pieces, because I have no global logging currently set up, failed to generate resource, and then it's trying to save the pack file. And yeah, it's writing the package file even through there are no data in it, but that's like doing it. But we have a problem, failed to generate resources, because the import triangular mesh generator was not found because it has not been properly registered. Now, how do we register it? Well, we need to uncomment this section here. Import triangular mesh, it needs to be registered. To be able to register it, we of course need to include that one. There is still some Assimp that we're gonna use later. So now let's include that one. RTR generators triangular mesh, g import triangular mesh.h. And now I'm going to say in here RTR generators g import triangular mesh. This is like expanding properly to a function call with like a function call to the generator registry, get the instance from that singleton, register a generator with like a template argument to that instance, and then the registry is gonna continue all of the live management of that actual generator instance. Now, if we're doing it like that, the generator is registered, and in theory it should be already called, and we should go into our breakpoint that we've just set, which we have done. We are now at a breakpoint in here. We are comparing the output of the console. We are still getting the same, but no error message. Now, if you're taking a look at that, you can see context.open to Suzanne.obj, and if we are taking a look at the geometry file down here, you can actually see that there is, since this is a file pointer, there is a base in here. The base is currently a RTR infrastructure physical file, and the physical file has been actually baked onto disk. Onto memory, I mean, but it's kind of like it's served from the physical file system, but it is even through already loaded completely into ROM. You can see that we are getting a file size, quite a big file, and we also get that file data. I can actually view that file data if I want to, and since it is an ASCII data, and you can see that we are seeing all the content of the OBJ file already loaded into here. So you can see, all right, the file loading was successful. And now what we need to do is we need to parse the file, because if I continue on, since we are returning false, we are getting an error generator import triangular mesh failed for resource whatever, and after that we get a message generator upload triangular mesh not found. Oh, I think I should have stopped there. This is a bug that I might need to fix. This should be fixable. Very simple. Core resources pipeline. That's actually a pipeline code. It's not that big currently, but I think where do I said that the generator failed? I think it should be somewhere down here. No, it's somewhere there. Generator failed for resource. Yeah, and we didn't return false yet. That's the problem. Return false so that we are doing an early return here. And now we shouldn't get that issue, but it's not a big of a deal. Now what we need to do is we now need to work with the geometry file. Now how can we work with that geometry file? Well, we want to open this up with Assimp, the open asset importer. And you know that I've already like stolen a few includes. Oh no, I've copied something else in there. Okay. Then we should have that one here, that include one here. Now if you want to use Assimp to just import some data, you're always going to need these three headers. You're going to need the importer, the asset importer. This is just a C++ class that helps you importing, because I think Assimp is a C library, and it is kind of like properly calling the C APIs down here and manages basically manages lifetime of the C object, so that we are using Assimp in the C++ style. Now what we then want to use is the Assimp scene. Assimp scene is the definition on how a file is kind of like laid out, because opening a geometry file in Assimp is always going to result in an Assimp scene. Assimp scene is kind of like the root file. It's including like all of its subfiles like types, textures, meshes, lights, cameras, materials, animations, metadata. It's like including everything that you need, and it defines somewhere down there. It should define a AI scene, a so-called Assimp scene. Down there is it, and the Assimp scene then contains stuff, but we're going to take a look at this as soon as we are having a Assimp scene ready, because it's always better to look at this in an interactive manner. Now, post-process is a special header. Post-process contains so-called post-processing steps or flags, however you want to call them, stored inside of an enum. Now, these post-processing steps are used to kind of like alter the data that you are importing. For example, we have calc tangent space. This can be used to calculate the tangent space of vertices. I'm going to get to that at some point, what the tangent space is. We also have something called join identical vertices. Now, what this one is doing, it tries to find vertices that are duplicated. And if they are duplicated, it's joining them together so that you are not wasting memory. You can see they are all extensively documented. If you do not know what they are, you can just read the text here. We also have something called make left-handed. This is kind of like going into the idea of left-handed and right-handed coordinate systems. So left-handed coordinate system, if I look for that, go to images and find the good old Microsoft image here and open this up, where you're going to find information about what left and right-handed coordinate systems are. Left-handed is kind of like with the z-axis pointing towards the screen, and right-handed is pointing out of the screen, the z-axis. Now, DirectX 12 uses left-handed, as you can see. Microsoft DirectX 3D uses a left-handed coordinate system. I'm also a big fan of left-handed coordinate systems. I'm the left-handed guy with Y up, X, Y, Z, exactly like Microsoft is showing that here. That's how I like my coordinate systems. And you, for example, have that flag here to make sure that it is going to be in that coordinate system. What you also have is the AI process triangulate. And now you are at the point, or we are at the point where we left off on Blender, where I told you that Suzanne could be triangulated using modifiers, or could be triangulated exporting it in Blender, but this is now the step where we want to put in triangulate. We could also do it in Blender, but this is the step that we should always have into real-time rendering. This AI process triangulate should be there, definitely, because it is doing magic. It's nice, it's amazing. Now you can also generate normals here, remove components, generate smooth normals, split large meshes, pre-transform vertices, limit bone weights, validate data structures, improve cache locality, remove redundant materials, fix infacing normal, populate, sort by, find degenerate, find invalid, generate chords, transform chords, find instance, optimize mesh, optimize graph, flip OVs, flip winding order, split by bone count, debone, global scale, embed textures, force gen normals, drop normals, gen bounding boxes, and so on. So Assimp has many options for importing, and now we just need to know how to do it. Now, how are we now using Assimp? Well, I have imported this importer, so let's use that one. Alright, so how do we use the Assimp importer? Very simple. Assimp, it's the namespace, importer, Assimp importer. And the importer is created. Now, what I can do is I can call functions on the importer. We have many of them. But what we are looking for is we are looking for read file. Now, read file has two options, read file and read file from memory. Now, the first read file takes a string to the file path. Well, our geometry file has pointers. We have close, get size, and read buffer. That's not really something that we can do. We do not have a file path. So what we actually want to do is we want to have the read file from memory function. The read file from memory function takes a void pointer as a buffer and a size t as a length. So that's very useful. Geometry file dot get buffer, geometry file dot get size. And we have all the data that Assimp needs. Now the next parameter are the flags. I'm just going to offload them into a new line. And they are called AI process. And we want to convert this to left-handed. Then we want to AI process triangulate. Triangulate. And we want to have AI process. We want to have AI process. How was it called? Join identical vertices is what we want to do. And I think this was the deprecated one. Yeah, that's not what I want to use. AI process, how was it called? This convert to left-handed. It was not convert, make left-handed. Okay, that's the one that we want to have. Make left-handed. AI process, make left-handed. There we go. And now we have opened up a file. Now what is this returning? It's returning us a const AI scene pointer. So I already told you everything in Assimp is going to be an AI scene what we import. So const AI scene pointer Assimp scene. Or actually let's call this object or geometry scene. This is going to be equal to that. So we could comment that one with open scene. Now what we could do is a bit of validation. If not geometry scene. If not geometry scene, we wanna do something. We wanna return false, obviously. And what I wanna do is a bit of logging. ctx get logger dot error failed to import geometry. Or we could say triangular mesh. Yeah, failed to import triangular mesh. Do we get some error information from Assimp? I'm not quite sure. We could try this out. Right. Assimp importer get error string. Yeah, we have an error string here. Failed to import triangular mesh. And then we can put in an error string in here. That Assimp importer get error string, and then we should have a bit of information on here. We could just try this by calling this maybe objx, which should be an invalid format, so Assimp should fail. I mean, actually this shall already fail. That's not a good idea, because this is like dereferencing a pointer, but it's not. Yeah, that's already gonna fail before that. Yeah, dereferencing null pointer. So if not geometry file, we might wanna return false here already, and wanna say something like ctx get logger error file not found. Now fail to import triangular mesh. Yeah, maybe let's put this one as well in here. File whatever not found. What file is that? Well, it's actually that file here. We are currently hard coding that. We should not hard code that. We should get or extract from properties. This is what we shall actually do. We shall not do this hard coded. So what I should do here is I should have an std file system path here, which is called my obj file. And this shall be, or actually we can just do this as a string, right? We don't care. This can be converted, cross-converted. Since it's coming from JSON, it's not a thing. We should also be able to get this here from the JSON straight away and convert this to std string like that. Now, how is the property called? It's called model file. That's very simple. And then I just gonna pass that one through. And then we can also output this in here. All right, so now let's see what this shall bring us. Now this shall bring us that the fail to import triangular mesh. This should be its information. Oh, it did not fail? Ah, yeah, because it's correctly specified in here. Need to modify it there. This shall now give us, okay, we have some problems in here. What's the problem? Why do the logger not set up correctly? Seems like the context's logger is not set up correctly. Because I again made some issue. Yeah, the context has not been set up correctly. Set logger. Get logger pointer. That's what I need to do so that the logger is attached properly. So that everything works. And this shall give us now some output. Failed to import triangular mesh files was an objx not found. Generator import triangular mesh failed for resource. Failed to generate resource. This is exactly what we want. We might we want to have a a logger attached per generator. No, I don't think so that we need that because we're getting the information of the generator here. All right, so I want to quickly simulate other behavior. For example, if we are trying to load the resource file as an obj file. Come on. If we would try something like that, then Assimp shall give us the error message actually. No suitable reader found for the file format of... Ooh. Interesting. Failed to import triangular mesh. No suitable reader found for the file format magic. Yeah, that's a nice error message. But it's coming from Assimp, so it's correct. I mean, if Assimp wants to give us such a cryptic error message, it's okay. But it's now coming from Assimp. That's good. Now let's actually fix this again. Like that. And make again a breakpoint in the generator here. Oh, there is a breakpoint already. And we could now take a look on what the AI scene actually is. Now we have the geometry scene and we can inspect what's inside of that scene. So I might want to cross-reference the actual implementation of AI scene so that you can take a look at this side by side. So the first thing that we get is some flags. We don't care about flags here. We also don't care about roots. The first thing that we care about is meshes. Now you can see that AI scene has m number meshes and m meshes as a pointer. So it's an array of meshes here, or an array of mesh pointers, and a number of meshes. So you can see in our case we have one mesh in here. And if we are taking a look at the first mesh, we can actually see that some data is attached to that mesh. And we're going to take a look at this in a second. I just want to quickly continue on what's also in here. You can see that we also can store materials in here with numbers and materials again. The concept is the same. You can see that we have two materials in here because Blender exported them. Didn't I uncheck that? Maybe not. Or maybe does it generate one by default if it's an OBJ? Can be. We can see that there is some data attached to it, right? Some material data. We don't care about materials. We can care about materials when you're getting to that. Same goes also for our animations. We don't care about that one, but we have them in here. Same convention, number and array of pointers. Same here with textures. Same with lights. Same with cameras. Same with metadata. And we also have a string name. So name, is there a name attached to it? Why is there no name attached to it? Oh, I don't care. Names are overrated. Right, our mesh has a name, but that's what we're going to see in a second, because that's what we are interested in, right? We wanted today talk about the mesh, so let's take a look at this. Let's go into the definition of the AI mesh. Now you can see the AI mesh works in a similar manner. You always have like a number and then an array. In this case, it's a proper array, actually, not an array of pointers. Now, what is inside of a mesh? You can see that there's also a hell of a lot of documentation. Assimp is really good documented. Also, you can learn something about models in general. But what we are kind of like interested in is kind of like the data that's attached here. Maybe I'm not going to go through that in the source code here. Now, we have vertices stored. You can see we have 1,966 vertices. That's actually quite some vertices. But yeah, you can see like these are all the vertices that are stored. In this case, 1,966 vertices. Alright, so I don't know why there are so many vertices now in here. However, I don't care because we want to just talk about the process of importing. That's something that I could fix. It's not a problem of Assimp. It's somewhere between me, Assimp, and Blender. An issue. But not because there's something wrong. Now we can also see that we have faces. Faces are not the actual triangles. 986. This is something that could quite be. However, that there are so many faces is a bit, vertices is a bit interesting. But maybe it's okay. Maybe it's okay even though there are so many. Now we can see that we actually have like m vertices. This is like the array of vertices. There's an array of normals, of tangents, of bitangents, of color information, of texture coordinates, number of UV components is also that's not an array. This is something that reference into the texture components. But yeah, you can see that here are something interesting. The faces now, it's also an array. Number of bones, pointer to bones, so an array of pointers. Material index, which material shall be used from the mesh. We have a name, and you can actually see that the name is actually populated with Suzanne. We have the number of animated meshes, or animation measures, but there's also none in here. M method, whatever that is also unused. What we have is a AABB. This is an axis aligned bounding box. That's a really interesting thing, right? Even though we don't need this, there's like a post-process flag that generates that one. AI process AAB. Generate bounding boxes. There we go. AI process generate bounding boxes. If I add that one in here, this value should be populated. This is just a side note that's completely unuseful now. But it's kind of like a box that tells the extent of the object. In this case, the mesh. You can see that now the AAB has now data in here. And we also have texture coordinate names. But that's also something that we are always not interested. The only thing that we care is number vertices, number of faces, vertices, and faces. Because faces are actually the indices. Now, as you can see, a vertex, it's just 3 coordinates. However, a face is storing the number of indices and the indices itself. So what it supports, since it also supports quad measures, is that in general every kind of like face, every like triangle, quad, line, point, whatever you have, it's like stored as a face. And each face kind of like stores the reference on how many indices it has. Normally, if we would have imported this raw OBJ without a triangulation flag, we would have gotten faces with 3 indices and faces with 4 indices. Now in this case, since we have provided the triangulate flag, we now have only faces with 3 indices, so we can always assume that. We don't need to assert this, we can assume it because we have set the flag. And these are all the informations that we need to extract this. Now I want to write the code so it is more usable for you. So the first thing that I want to now do is I want to now index the mesh. How do I index the mesh? Well, I need another property. I need a int property, mesh index. The mesh index is going to come from the properties as well, and it's going to be converted as an integer, like that. Now, how's the property called? I think I just called it mesh, right? Resource.json, yeah, mesh and then 0. Now, how can I get the index and validate that one? Very simple. If index smaller than 0, or index bigger equal geometry scene. Is it the pointer? Yeah, it is. M number of meshes. So if it's bigger equal meshes or smaller than 0, we're gonna say context get logger error mesh index whatever out of whatever mesh index whatever out of bounds. Ausrufezeichen. Of course, we want to also have the text here, failed to load triangulated mesh. Now we just need that one, mesh index out of geometry scene num meshes. That's now validated and we can return false here. Now we have kind of like validated the mesh and now we can index it. So const AI mesh pointer geometry mesh. It's going to be equal to geometry scene meshes at mesh index. Now we have the mesh here. Now in the next step what we need to do is we now need to extract counts from the geometry here. How can we extract the counts? Well, it's very simple. I want to actually store them as size t now. Vertex count, it's going to be equal to geometry mesh number vertices. Yeah, it should be vertice count, but yeah, vertices count. Size t index count. Index is, yeah, it's a bit different now because now this one needs to be calculated. Why do we need to calculate that one? Because we need to get the number of faces and multiply them by 3, because every trace is gonna have multiple counts. I'm just gonna call it one vertex count, vertex and index. I like the name more. I know why. And now what I want to do is I want to make a quick breakpoint here and quickly see if everything works as expected. Let's see. And what we're gonna get here is we're gonna get an index count. Yeah, here 2904. And the vertex count 1966. That's good. These are correct counts. And what we can also do is we can validate our code a bit. We could make something like the index 5 out of that without deleting it by accidentally pressing some key combinations. Now we should not hit the breakpoint, and we should get an output here. Mesh index 4 of 1 out of bounds. Yeah, maybe we want to have it in that format. It's maybe a bit confusing because now 1 of 1 would be also out of bounds, but if we are programmers, we know what we do. Right, and also negative values, they should also not work. That's just -1 because it's like the edge case after 0. But still, we're gonna get the proper output here so that everything is good. Now let's revert it to the correct one, and let's now continue on exploring how we can do them. So now what we need to do is we now need to actually output data. And since we shall never work with the file system, because every generator is like working on a context and it's all nicely bound together, we actually need to ask the context to do something for us. In this case, what we want to do is we want to allocate output data. Now, our output data is a quite useful thing because this can be multiple things. First, we need to define a name for that because they need to be named. In this case, it's going to be the vertex buffer, and we shall always name them like a file, even though this might not be stored as a file. So vertex buffer.bin, because it's a binary format. The size is going to be the vertex count, and then the usage needs to be defined. Now we have multiple usages that are available. Now the usages define how it's going to be used. We have pipeline target NC and pipeline target IC. Pipeline target is always going to be the final target of the pipeline. So for example, if we have a generator that uploads data to the GPU and it's like the final target of the resource, the end of the target, it's going to be a pipeline target. If we are uploading it to the GPU, it's going to be a pipeline target NC, pipeline target non-cached. Because if we upload something to the GPU, it's in a format that's like valid for the GPU, it's uploaded on the GPU, it's in VRAM, we can't like access it, so it shall not be cached. Even though we would never have something like that. But we might have something, right? We might have some compiled pipeline state object that might be reloadable but shall not be cached. I know there could be anything that is being used here, but this means non-cached, and IC means is cached. It could be that a special resource is a target but is also cached. Now, what we have is the pipeline output. Pipeline output is everything that shall be outputted out of the pipeline, but it's not at the end of the pipeline. This is exactly what we have. We have one step here that shall be outputted, even through, especially because we are using it for baking. For baking, it needs to be outputted because it needs to be reloaded, and it basically just stands for pipeline artifact. It's a pipeline artifact that shall just be outputted to the cache directory so that it can be reloaded or later on packed. Pipeline intermediate, on the other hand, it is something that shall never be cached. And in this case, if we are using allocate output data, it's never going to be a file, even through its kind of like reference is vertex buffer.bin. But if it's a pipeline intermediate, it's never going to be outputted as a file. It's just going to be an internal void pointer stored somewhere and fed into the next pipeline if it needs that. And the next pipeline can then open this with the context.open function, and it's not going to getting a virtual and physical file, it's going to get a virtual file. But in this case, we want to output that, so we're going to specify pipeline output here. Now you're going to see one big mistake. The vertex count is not implying any size. It's just a count. To imply a size, we actually need to know how a vertex looks like. And normally you would define this properly, but I'm going to just temporarily define this here. So I'm going to define me a public struct vertex. And the vertex is just going to get 4 floats, x, y, z, and w here to define a vertex. It's just a simple representation here to kind of like have a format for that. And as soon as we have something valid to that, we can use the templated version, vertex. And now we are working with proper counts. Now it's changed from size to count, or should have changed. That's not reflecting that, but it should. Or did I forgot to name that one count? No, it should be count, but it's kind of like picking the wrong definition. But it is count because we're using the templated version, right? Okay, and what's that basically allocating is it is allocating myself the vertex buffer. So I'm going to call this one. No, I'm calling this vertex data because the vertex buffer implies that it kind of like lives on a GPU, but it's not in that case. So let's maybe make this like that so that we can see it on the video a bit better. And now what we need to do is we need to do the same thing for the indices. Now for that, I'm already spoiling something. Indices are going to be 32-bit values because the GPU is a 32-bit processor, and this is why indices are going to be uint 32t of a type. So index data going to be equal to context allocate output data for uint 32t. In this case, I'm going to call this one index buffer.bin, not .bib, bin, index count, not interface, visual assist, you sometimes suck. Yeah. Then in this case, it's also pipeline intermediate because it's also outputted and cached. And this is everything we need. Now we can work with this buffer and everything else is handled automatically. We do not need to free them. We do not need to memory manage them. We allocate them, we work with them, done. So extract count, or maybe let's say allocate output. And now what we can do is we can work with that. And first of all, let me extract vertices. Now, how do I extract the vertices? Very simple. For size t I in it's going to be 0, I smaller vertex count, plus I, and then we want to now actually extract the vertices. How do I extract the vertices? It's going to be very simple, the code for that. First of all, I'm going to go to my vertex data at the position I, and it's going to be equal to something that I'm going to extract. What do I'm going to extract? I'm going to extract the AI vector 3D. The AI vector 3D is a type that defines a three-dimensional float vector. You can see AI vector 3T, AI real. This is kind of like float. And what I want to do is I want to get this from the geometry mesh. So the geometry mesh has the M vertices, and M vertices at position I is going to be that specific vertex. Now what I can do is I can extract the vertex data. So I have an X in here, I have a Y in here, I have a Z in here, and since it's a point, it's going to be 1.f for being 1 as a vertex. Alright, and that's everything that we need to do to extract vertices. Next thing that I need to do is extract indices. Now, how do I extract the indices? That's a bit more involved. For that one, I need to iterate over not the index count. No, I actually need to iterate over the m numbers of faces, so the number of faces in the in the uh, in the mesh. And what I need to do is I need to access that face. So AI face reference face equals geometry mesh m faces at position I. So now we have a reference to that face. And now we can see that the face has indices and we could access them like an array, right? So index 0, 1, and 2, we can access them. And where we want to store them is at the index data, and it shall be directly stored at like 0, 1, and 2. As simple as that. However, we cannot do that because we still need to reference I. So this is actually going to be an offset that's going to be applied to that. And what's going to be the base? It's going to be E times 3 because every face is going to contain 3 or every 3 indices. So we can do this by E times 3 plus 0 plus 1 plus 2 and access the proper index data. And if everything was successfully, then we can return true. I don't know if do we have a free function on the Assimp importer? Do I need to call free on that? There's nothing that I need to call, so everything is good. We do not need to free that. That's what I thought, but I just wanted to validate. Now that's everything that we'll need, and this is also already providing now a full chain implementation of all of that. Now, if I run that, we should already get the data correctly. I can make a breakpoint here. Yeah. Just to show you that everything goes through. But what's happening now is that we have basically the vertex data, and you can see that we already have a vertex populated here. We also have the index data. The first index is 0. We could open this up in like a memory view to get a few more insights on that, and we should see that it's like continuously stream that's going to grow in its number. At some point it's going to be completely 0, but that's not really the point that I want to show here. But it's working. It has iterated through that. We don't have any error message and everything is good. Or do we have error messages? No, we don't. Now what I can do is I can click continue on and it would work. However, you can see that we still can find the upload triangular mesh generator. So let's actually now implement that one as well. This is not going to do anything because we don't have the code for that, but we can already bootstrap the code for it and return true just so that everything goes through. So g upload triangular mesh. Let's create a namespace RTR generators, and let's make a class in here, g upload triangular mesh. Now I'm gonna go to that one here to just gonna give me some starter template. I don't really would have need to do that. Yeah. So this is a public resource generator. Then we can create a file. Then we can go in here, go to implement virtual methods, implement them down in here. I don't like how they formatted through that functionality of Visual Assist, but yeah. And there we go. Now I can return the name. G-upload triangular mesh so that we know that everything is good. And down here I can return true. However, what I also want to do quickly is I want to have like my vertex data. I want to get them here as well. So we can actually call the context and open my vertex buffer.bin and index buffer.bin vertex data index data, and then I just make a breakpoint here so that you can see that all works. Of course, generators need to be registered, so what I'm doing is I'm adding the registration for that one as well, and I'm gonna include this one with g upload triangular mesh. Actually, did I remove the g here? Yeah, I did. What I can do now here is add that one in here as well. and add the G here because the G was missing. And now we have both of these generators registered, and now it should properly work. Let's see if we hit our breakpoint correctly and have the data attached to it. And we do hit our breakpoint, and if we would take a look at this, you can actually see that there is a virtual file now backing that up, so it's actually now a virtual file. Virtual file means that it is not a file that's like baked by the file system. It's not a pointer that it's owning. It's like somewhere else stored. This is why it's a difference here. But you can see that there's like a data attached to it. For example, if I would go to, is that the vertex data? Yeah, that's like the index data, because we're already taking a look at this, and you can see that we can find the same index data that we had previously, or should have. The exactly same data that we had previously, and everything is good. Now, if I continue that on, you can actually see that everything shall be executed correctly. So you can see executing 2 generators for resource, dumping cache file vertex buffer bin for resource. Interesting. Dumping cache file vertex buffer, but I do not have a dumping cache file index buffer. Why do I have no index buffer? Oh, pipeline intermediate. It shall be pipeline output. Yeah, that's why it hasn't cached it, because it was marked as an intermediate. If I have both with pipeline output, we should get a proper output with what the? Oh, because we don't have a breakpoint. Yeah. Let's continue on. Now you can see that we are dumping these 2 cache files, vertex and index buffer. And if I would take a look at my cache directory, you can actually see that we have that index buffer.bin and that vertex buffer.bin. If I would reveal them, and for example, take a look at the index buffer, show more options. I would go into my hex editor. Please beware of your eyes. There we go. Can I zoom in here? No, I can't. But if I would take a look at my of the view, you can actually see that we have the same format that we also applied, like these quad parts that are kind of like going up and up. You can see that basically the data is correctly in there. It's the same data that we previously had in on disk on memory later on. It's now exactly dumped to memory, to disk. I'm confused currently, but yeah. And it's probably stored in like a cache directory. Now, you're not too concerned about the cache, but I am concerned about them. They are just stored like that. Later on, this cache info is going to be populated, but it's currently not. Now, since all of these cache is populated, what I can do now is I can actually now convert this into a pack file. You can see that I'm currently generating this for the editor. If I just add another call to that, and instead of editor once generate this for the runtime, or what I could also do is I could do first bake and then runtime, because this would now more or less kind of like follow the scheme that I'm using. First baking, then runtime. Then it would be a bit more on how this would work, but I do want to have it kind of like editor and runtime. But if I do it like that, I should maybe have baking here as well, so then we have like everything tried out here. It should now probably invoke like every of our generator twice, but that's not really such a big of a deal yet. So we should get an extensive log output here, collecting for editor. I can see that the editor was importing and uploading, baking was importing, runtime was uploading, and now you can actually also see that we have information from the pieces here, processing file, the cache file here. Basically, the name of the file is whatever resource ID that is, vertex buffer bin with a compression applied to it, and index buffer with a compression applied to it, which has been outputted to this pack64 file. And if we're taking a look at this, we actually have this. No, should be in the cache here, output pack64. And this is now actually the file that's later on going to be shipped. You can see that it's 18 kilobytes big, and these 2 files are in there, which are in total 42 kilobytes. So 42 kilobytes has been compressed into 80 kilobytes. And we can now actually take a look on how this looks. And this is how this looks. This is my pack64. file format that I have created, inspired by the Dooms file format. Basically down here we have a bit of information on where this is stored, vertex buffer.bin, index buffer.bin, and a few informations on where it's stored and how it's compressed. For example, like this 8.1 hexadecimal stands for the compression mode. Then we have like a thing like the compressed size, uncompressed size, and this should be the offset where it's stored, which should be somewhere there. Yeah, that Ö. And this is some LZ4 compressed data of these binary buffers. And it's all implemented. It can automatically load from that file as well. This is just like the idea that this gets all automatically mangled into correct file formats. Because what I want to do is I want to later on ship your demo applications. That's why I'm doing this. Every video later on shall have a demo application that I show you, and then we're going to explain it and get to that, and you shall be able to download these applications and view them on your system and play with them around. That's the idea. You just get this PUC file with everything included, properly baked into data formats here. All right, so I promised to you we're also going to do it with FBX. Yeah, sure, it's not a problem. I'm going to export this as an FBX. Object types, we just going to export everything. So just so you can see, I know we can do everything. Forward, a Y up, and we're going to do again Z forward. Yeah, bake animations. Yeah, okay, we do this. That's still not, why are you not... it doesn't like to remember my path. Let's go to my data directory again. Let's call it Suzanne.fbx, export fbx, fbx export done. Now we have Suzanne.fbx. You can see that the fbx is way smaller, even though more data is in here, because we now have also the camera and the light. We didn't have that one in the OBJ, but since fbx is a binary format, it's smaller. And if I go in here, the general idea is that the only thing you need to do is you need to change that from Suzanne.obj to Suzanne.fbx. And what I want to quickly do is I want to rename that to .old.packfear so that you kind of like see the difference. And if I now rerun this, the general idea is that everything goes through without any issues. And we are producing the same PUC file. This PUC file shouldn't have changed at all. Now, actually, they have changed. I have just compared them. They have actually changed quite a big one. This is because FBX is using different exporters in Blenders and different importer in Assimp, so the order is different, the rounding might be different, and even though we are getting the same object, maybe we're going to later on compare them. Now we have both of them, the FBX file and the OBJ file. Maybe we're going to compare them later and see what the difference between these two files are. But in general, from a visual aspect, they shouldn't be too different. You can see maybe a few less vertices, maybe a bit more optimized, since the file size is different a bit, 17.2 versus 16.7, so half a kilobyte more for the OBJ one. But yeah, that's really not something that we care about, right? The main thing is it's completely doing the same. If we are doing it with OBJs or if we are doing it with FBX. So that's the whole idea. We don't care about OBJ or FBX. So yeah, this was quite a long video actually for the implementations. I hope it was useful for you and it was easy to understand, also to understand how the system works and how these resource generators works. And yeah, you can see it's simply just open, allocating data, as simple as that, and everything is done in the background automatically, especially like caching, calling these generators and skipping generators if they don't need to be called. That's all something that I'm going to handle, and including hot reloading. So yeah, thank you for watching. See you in the next video. Make sure to like and subscribe, and have a nice day. Bye.